the beginning of America's decline as far as I was concerned. I mean, its highlight was when America put a man on the moon. That was America in its full glory as far as the world was concerned. And similar story with, well, debatable, with nuclear fusion research. I mean, the world's most powerful tokamak, it's a kind of magnetic torus, like a magnetic donut, a hollow donut that traps ionized gas inside it to generate nuclear fusion. That too transferred to Europe because America wasn't willing to pay for it. America's doing other stuff like superpowered lasers to generate nuclear fusion as well. But I don't know, America seems to have lost its vision, lost its energy. And one of the reasons I'm living in China is, you know, it'll take time. Today's China, I mean, be blunt, today's China is a shithole, quite unfit for Westerners to live in. So, you know, don't come here. But you know, its momentum is superior. Its position is inferior to the West, but its momentum is greatly superior. So I calculate 10 years or so, China will democratize, then have freedom of speech, and then 300 million, 30 million. So anyway, multiple tens of millions of Chinese intellectuals will then be free to express themselves. And I'm expecting in the 2020s and 2030s, if I'm still alive, China's intellectual level will make this, you know, China, the most exciting place on the planet. That's what I'm here for. Well, the immediate reason is because China's poor. So my American savings go further, so I can afford to retire earlier, and therefore I can be free to do what I want earlier, and I consider making YouTube videos at graduate level hugely more significant than what I was doing before as a professor, teaching small classes, writing research papers that statistically were virtually unread because only one person on average reads a published research paper in journals and proceedings of conferences. So somewhat cynical of past life. Anyway, okay, so, alright, so we have the current flowing down the wire, we have the compass needle that is disturbed when the current starts to flow, it stops. So of course people started investigating you know, this phenomenon. Like an obvious question is, well, how strong? So in other words, this current is generating a magnetic field, right? Because it's magnetic fields that make the compass needle turn. You know, it points to the north. That's because the Earth generates a magnetic field. There's a north and south pole, magnetic north and south pole of the Earth, right? So one obvious question is, well, how does the magnetic field generated by this current, it appears, how does it drop off with distance? And here's the formula that was found. It's some constant. It depends on the current. That's sort of common sense, right? You put more current, you expect a strong magnetic field. So, you know, it depends on the current, and it drops off as the distance, just r. Okay. So this is one of the famous formula from electromagnetic theory. So, you know, here it gets used. I'm trying to remember, it's been a while since I've done undergrad electromagnetic theory. Is it the BO, you know, French B-I-O-T, Savart, S-A-V-A-R-T law? Maybe, you know, I may have that wrong. You know, I'll teach a course on electromagnetic theory. Anyway, here's a formula relating the strength of the magnetic field at distance r from the wire, you know, perpendicular distance from the wire. Right? Here's the wire, here's your point, and this is your distance r. Okay, so we have this magnetic field r with this formula, right? So now we know the formula for the current. That was this, right? So just plug this value here into this equation. So you now have an equation relating the magnetic field strength B to these factors. Right? B is just this by plugging this for I into here. So B equals this, right? Now the magnetic field, if you want the direct, that's the size of the magnetic field, but if you want its direction, which way is it oriented? Well, then you have a vector equation here. So now treating the magnetic field as a vector, so a strength, that's the scalar, and you give it a direction, so hence a little wiggle to make it a magnetic field. It's turning into an undergrad lecture, right? Well, it is, sorry. Sorry. When I conceived this whole thing, I was so, deGarisMPC, I was so oriented towards that it, strongly committed that it would be a graduate level course, because all my life I'm pissed off with seeing societies so uncaring towards the sages and the soups. So I really wanted to do something particularly for the sages, well, the alphas, particularly for the alphas. So I really wanted to do graduate level now, but for practical reasons, so that alphas can teach themselves up to graduate level. That's virtually impossible if I just start at graduate level. So necessity forced me to commit myself to teaching about a dozen or so undergraduate level courses, of which this is one, quantum mechanics, basic topic in physics. So, but in practice, for a year or so of my life now, I'm going to be teaching undergrad stuff. So, yeah, c'est la vie. All right. So, to turn the magnetic field into a vector equation, a vector quantity, you need a vector quantity on the right-hand side, and you can do that by taking the cross product of the velocity now, which way is the nucleus spinning, so give it a velocity, and this is now your position vector from, which way is it? That would, I think that is from the nucleus to the electron, okay, in that direction, that orientation. Now r cubed, so you've got an r squared here, and r cubed because you've got an r here, magnitude. And the result of that cross product will give you the direction of B. Okay? So we now have the vector B. Now, knowing vector B, we can dot product it with the... oh, wait a minute, I'm getting a little ahead of myself. Alright, now we can rewrite this B in terms of other things that we know from classical mechanics. Now, one is the angular momentum is, well, there's the momentum there of the electron. So little m.e, that's not a c, that's a little e there, so the mass of the electron times the velocity, its velocity times cross product r. So this is a vector angular momentum. Okay, so this is just the momentum, mv times r, and a cross product to give it a direction. Okay, so we have here a formula for L in terms of classical quantities. Now, look on, if you take the potential the Coulomb potential, it's a charge divided by 4 pi eta, it's basically a constant, over r. That's the Coulomb potential. So if you differentiate it with respect to r, you'll get this r squared underneath, right? So you can rewrite that as dV by dr, and that's the force. That's the force on the electron from what? From the Coulomb potential. Okay, so. A potential, you can think of a potential if you differentiate, you get a force. That's sort of general notion of a potential. Okay, so dV by dr is this quantity here, which is the force on the electron. Well, there are a few other factors in the next session that we'll bring in, and then finally we will rewrite this vector magnetic expression in terms of these sorts of things, which we will then use to find the potential energy due to the spin-orbit interaction, and then we can add that potential energy term as a perturbation, a slight change in. We can add it to the Hamiltonian, and then get changes in the energy eigenvalues and so forth. So that's what's coming the next couple of sessions.